So what we'll do in the first hour is continue with the new SM, the standard model extended, or with the dimension 5 non-renormalizable terms. And let's do one more model that I will explain related to neutrino masses. And that's 1 hour. Then we'll do tea break, which is a good part of the day. And then we'll do the second hour. We'll start a little bit of particle cosmology, as much time as I have. Dark matter, baryon asymmetry, we'll see what we can have of these. And we stopped yesterday with the neutrino spectrum and adding dimension 5 terms to the standard model, or these non-normalizable terms. The main effect is that it gives neutrino masses, and very nicely it gives them masses that are on a scale much lighter than of all the other standard model, massive standard model particles. All the standard model particles that have mass, the mass scale is V, and for this now it's V squared over lambda, which by definition is much lighter than V, because lambda by definition is a scale much higher than the electroweak scale. So we have in this framework not only an explanation of the neutrino masses, but also of why they are much lighter than all the other particles, which make this a very plausible explanation or source of neutrino masses. And it implies that they are Majorana neutrinos. But that's a theoretical thing, not yet an experimental. So we can move on. We did the spectrum. The change from before is 3 very light neutrinos. Let's see about their interactions. So again, these LL5 terms involve essentially only the neutrinos and the Higgs, so we'll see about that. Neutrinos do not couple to the gluon. They are singlets of SU3 color. They do not couple to the photon. They have no electromagnetic charge. So there is no effect on the strong or electromagnetic interaction in this extension of the renormalizable standard model. Before there were mass eigenstates, we could see the Z interaction with the neutrinos at any basis, and they were universal. Now we have to move to the neutrino mass eigenstate basis, neutrino 1, neutrino 2, neutrino 3, and it's easy to see, I don't do it here, that the Z interactions remain universal in the mass basis for the neutrinos. So there is nothing new here, except that now we moved from Ni E, Ni mu, Ni tau to Ni 1, Ni 2, and Ni 3. And what's interesting, I think, on the level of principle, but perhaps not practically observable, is the modification for Yukawa interactions. So in the renormalizable standard model, the neutrinos are massless, and they do not couple to the Higgs. They don't have Yukawa interactions with the Higgs, and that's related to their masslessness. Now these dimension 5 terms, LL5, give us not only neutrino masses, but also Yukawa interactions. There is an interaction, a usual Yukawa thing, or almost usual, a single Higgs field and 2 neutrino fields, and also a coupling. Since these are non-normalizable, you can have this type of thing, 2 Higgs fields and 2 neutrinos. And these interactions are still diagonal and not universal, the same as for the charge fermions, and proportional to the mass, the same as for the charge fermions. The Yukawa couplings here are particularly tiny, so they are proportional to the neutrino mass over V, which is 10 to the minus 12 and smaller. So these are extremely small Yukawa interactions. When I say that it's not of practical implication, it's because of that. We will not observe it. But there are two interesting things here. First, it's not the Majorana nature of the neutrinos is also here. This Yukawa coupling violates total lepton number by 2 units. Okay, it's not psi bar psi. It's neutrino neutrino. Okay, 2 neutrinos. And the second thing is that while these Yukawas are proportional to the mass, as for the charged fermions, the proportionality factor is different. In the charged fermion, it was square root of 2 over V, and here it's 2 over V. Again, has to do with the source that is different, it's dimension 5 terms. If we could have measured the Yukawa couplings, they would not, the 3 neutrinos would lie on a straight line, but it will have a different slope than that of charged fermions because this proportionality factor is different by square root of 2. But we cannot measure, so we can just imagine this plot. Yes?
So that interaction LHD is not a new bar of T, it's just new.
Again, which interaction?
The new I, right?
Here, yes.
So it's not a bar over that.
Right, it's not a bar.
But then how is it a scalar? Okay, so then how will it be a scalar? That's what
there are, I always forget where the chalk is, and then I do 360 degrees round and find it. So the combinations that can make a Lorentz singlet of 2 fermions are not just L bar, right? But also LL and right. And this is LL.
It's LL.
Yes.
Okay.
See, if it's possible to have a mass term, not the H here, but M, then it's also possible to have a scalar here. A number, a mass, and a scalar field transform in the same way under Lorentz. So these two combinations are the combinations that enter Majorana masses, and they can also enter a Yukawa coupling because these can be contracted to a singlet of the Lorentz group. Okay. So that was for the Z, no change. For the Yukawa, yes, there is a change. It was 0, and the renormalizable standard model, it's different from 0, has interesting features, and it's unfortunate that we will not see it in experiment because it would have been nice to see another straight line, and that would have proven the Majorana nature or even the source from this dimension 5 terms, but we cannot do it experimentally. Where there is a big difference is in the W-mediated interactions. The charge current makes it, the charge current weak interactions. So in the renormalizable standard model, the W couplings to the leptons were universal. Ni bar E, ni mu bar mu, ni tau bar tau, with the same coefficient G over square root of 2. And this was because there was an interaction basis that was simultaneously the mass basis for charged leptons and for the neutrinos, and that was a result of the fact that neutrinos were massless in the renormalizable standard model, and any rotation of the basis for neutrinos is there a mass basis. Now they are not degenerate, and so similar to the quark sector, there is now no interaction basis that is simultaneously mass basis for charged lepton and mass basis for the neutrinos. The transformation that you take the 3 left-handed lepton doublets, LL1, LL2, LL3, into the mass eigenstates of the charged leptons, E left, mu left, tau left, is accompanied by it's a unitary transformation with VE left from the left. The transformation that takes from the same interaction basis, the transformation of the 3 left-handed lepton doublets to the neutrino mass basis is a different, in general, matrix VD left. Both are unitary matrices. So to go from this in the interaction basis, where this is universal, to the mass basis, you have an insertion of VE left here, an insertion of VE left dagger here, and so this together, VE left dagger puts here a mixing matrix U, which is the analog of the CKM matrix in the quark sector. The same thing now happens also in the leptonic sector, which makes the leptonic charge current big interactions in this extension of the initial 5 terms of the renormalizable standard model. Now they are neither universal nor diagonal. So that's a big change from the renormalizable standard model, related to the fact that the neutrinos are now massive and not degenerate. And so, similar to the quark sector, these diagonalizing matrices depend on the basis from which we started. This combination is invariant to that. It's independent of the choice of the interaction basis. It's always the same. The elements here, so these are the names of, on the left we have charged leptons, the mass eigenstates, E, mu, and tau, so these are the columns. And on the right, there are the neutrino mass eigenstates, 1, 2, and 3. So this is the leptonic mixing matrix, also called sometimes the PMNS matrix. For 1, Bulgarian, Pontecorvo, and 3 Japanese scientists that he introduced the idea of oscillations, and the 3 of these suggested the first mixing matrix, but in the context of a different model, actually. So here is the new SM lepton interactions, electromagnetic, universal, only among the charged leptons, neutral current weak, universal, both in the charged lepton and neutrino sector, charge current weak, now similar to the quarks with a unitary matrix for these pairs, and the Yukawa, which is proportional to the mass, so it's diagonal, proportional to the mass, but with a new proportionality factor. Next step, accidental symmetries. They are always a subgroup of the symmetry of the kinetic terms, which is this U3 to the 5th. In the mentioned 4 terms, the renormalizable terms, the Yukawa broke it into U1 to the 4th, U1 baryon number, electron number, U number, tau number. Now with these additional LL phi terms, all the 3 lepton symmetries, E, mu, and tau, and even their sum, the total lepton number, are broken, and this model has left as an accidental symmetry a single U1 baryon number, where the quarks have charge a third and all other fields are neutral. So it breaks what we call lepton, there is here lepton flavor violation. Electron number can change, mu number can change, tau number can change. That's flavor violation, lepton flavor violation, and also lepton number violation. The number of leptons minus antileptons in the initial state and leptons and antileptons in the final state can be different, these numbers. Now, experiments, the neutrino oscillations experiment, established that all 3 flavor symmetries are violated. U1E is not conserved, U1 mu is not conserved, U1 tau, we've seen that in experiment. We did not see yet in experiment violation of total lepton number. The neutrino oscillation experiment conserved lepton number, so we did not see that yet. This model predicts that it is violated, but you need a different kind of experiment, not neutrino oscillations, but the most likely to discover violation of lepton number is neutrinoless double beta decays. parameters. Again, it goes here through this method of counting how many physical parameters there are. In the lepton sector, in the renormalizable standard model, there were only 3 parameters, the charged lepton masses, or the charged lepton Yukawa couplings, ME, MU, and tau, or equivalently YE, Y mu, Y tau. And now we have 9 additional parameters, the 3 neutrino masses. In this mixing matrix U, there are 3 mixing angles, 3 real parameters, and different from the CKM matrix, which had 1 imaginary parameter. Here there are 3 imaginary parameters. This is related to the Majorana nature of neutrinos. In the quark sector, you can redefine the phases of the quarks, maintaining the quark masses real and removing phases from the mixing matrix. Here, since the neutrinos are Majorana, redefining their masses introduces phases into their masses. You don't want to do it, and so you cannot redefine the neutrino phases, and that's why you are left with 3 phases. If you are working on this topic, you should do this exercise explicitly to see how it's working. But we have here 3 new sources of CP violation, and actually, not sure whether it's mentioned. Actually, the phases in the leptonic sector, in particular the one that is the analog of the Kobayashi-Maskawa phase, are interesting. So these things can be relevant to a scenario that solves the baryon asymmetry problem by a scenario that is called leptogenesis. I may come back to it in the next hour, but that's why CP violation in this sector is interesting and pursued by experiment to establish whether it's there. But so the newest M, so to remind you, the standard model has 18 parameters, the newest M has 27. And of the 9 new parameters, we've measured 5. The 3 mixing angle in U are all measured, and 2 mass square difference for the neutrino masses are measured. We don't yet know the absolute scale, and we don't yet know the phases. So in the newest M, we still miss 4 parameters. We don't know them yet. It's likely that in the not too far future, we will know 2 more out of these 4. We may know the phase that is the equivalent or the analog of the Kobayashi-Maskawa phase, and we may know what is the absolute scale of neutrinos. We'll see. Yeah, let me just mention here one thing. So in the CKM matrix, it's very close to being a unit matrix. All the off-diagonal terms are small in CKM experimentally, and the diagonal terms are very close to 1. This is not at all the case for the leptonic mixing matrix. Sinus square being 0.3 implies that this entry here is of order 0.58 or something. This S23 implies that square 0.56 means that this is of order 0.7. So the off-diagonal terms, except this which is a little small, are order 1. We don't know a priori, these are independent parameters. It has been somewhat surprising to the community that mixing angles in the quark sector of diagonal terms are very small, and here they are order 1. It may be a hint to some mechanism that determines the size of these things, but we are not sure how to interpret this difference between the lepton sector and the quark sector. So we still don't know the Dirac phase. It's a major goal of future experiment, particularly out of Dune. And the Majorana phases, very difficult to see how we will know them. Affects only lepton number violating processes. So they play a role in neutrinoless double beta decay, which is violating lepton number, and we may know something about them if this is observed. So how can we gain further support to the idea that these dimension 5 terms are the source of neutrino masses? The first thing is neutrinoless double beta decay. We would like to see a signal here, to know that lepton number is violated in nature. This will be a very strong support beyond the fact that neutrinos have masses and they are very light, which support this idea. This will give a further strong support. In the contrary, there is also search for lepton flavor violation in various decays of charged leptons, or the Z, or the Higgs. The newest M predicts that all of these go, but at rates that are branching ratio, something like, I don't know, 10 to the minus 50 or so to this, so completely unobservable. So if we observe any of these, it will mean that there are sources of lepton flavor violation that are not included in the newest M. So observing this will exclude the idea that that's it, that explains all that we see, in particular that the newest M is the only source of the breaking of U1E cross U1 mu cross U1 tau. It cannot explain if any of these happens in a rate that is observable to current experiments. And this goes back to the scales of beyond the standard model. The neutrino masses in this model are v squared over lambda times diagonal entries of this matrix there. So actually the community, which we think that the standard model is effective field theory, we should include this term before discovery of neutrino masses. And since we know that the scale, the cutoff scale of the standard model, the highest possible is the Planck scale, it gives kind of a lower bound on what to expect from neutrino masses even before we measure them, and that's of the order of 10 to the minus 5 electron volt. So if we search for neutrino masses and will not find them up to 10 to the minus 5 or so electron volt, it should have been surprising to us. We should not have expected that neutrino masses are really zero, because we know that the standard model is a low energy effective theory, also for other reasons, and then this is kind of the minimum where they should have resided. If you think that there is grand unification, so that there is a scale of new physics at around 10 to the 15 or 10 to the 16 GeV, we should have expected their scale to even be higher than this lower limit, around 10 to the minus 2 electron volt. Now we reverse, here is what we may have thought about the scale of new physics and what it applies to neutrinos. Now we know what the neutrino masses are, so let us use that to say something about the scale of new physics. We know that there is at least one neutrino heavier than 0.05 electron volt, the square root of the largest mass square difference, and that puts an upper bound on the scale. It's v squared over mn. We know mn is larger than something, so we know that the scale is smaller than something, and that's 10 to the 15 GeV. So we learned in this framework on a new scale in physics. If the Z couplings are for some reason small, then the scale would be even lower. This is an upper bound. This is if the couplings there, the dimensionless couplings that are relevant are order 1, then the scale is 10 to the 15 GeV. If they are smaller, then it would be even lower. So we learn on a new scale. It's significant that it's below the Planck scale. It's a proof, for me at least, that there is a scale of quantum field theory below the Planck scale where the standard model above which is not longer a valid theory and it's only a low energy effective theory. That's the strongest proof of that statement. but also it's extremely close to the grand unification scale, and maybe it's not an accident. Almost all grand unified theories predict exactly this, they generate effectively these dimension 5 terms and predict that neutrinos are massive with a mass scale which is v squared over m gat. So maybe it's a supporting hint that there may be grand unification in nature, the proximity of these two scales. So here's a summary of the new SM. I think all particle physics results of terrestrial experiments. Okay, so putting aside cosmology for the moment, are accounted for in this framework. The renormalizable standard model is not because of neutrino masses, but the new SM is. So here was the definition of the model, the same 3 lines as the standard model, but now we added the dimension 5 terms. The Lagrangian was the renormalizable standard model Lagrangian, plus a set of dimension 5 terms involving 2 scalar fields and 2 lepton doublets. And the difference from the standard model in the spectrum was that we now have 3 neutrinos mass eigenstate. They have masses and can be distinguished by their masses. So this is the new entry, and the names here, Ni1, Ni2, Ni3, while before it was Ni, Ni mu, Ni tau. The interactions, the change is in the charge current weak interactions, where it's no longer universal, but has a unitary matrix for the various pairs of charged leptons and neutrinos. And the Yukawas are also changed. Now also the neutrinos have Yukawa couplings. They are still diagonal, proportional to the masses, different factor of proportionality. The accidental symmetry is smaller than the one. It's a subgroup of the one of the renormalizable standard model. We are left only with baryon number, and we have 9 new parameters, 3 neutrino masses, 3 real mixing angles of the leptonic mixing matrix, and 3 phases, all of these characterizing the W interactions with pairs of charged leptons and neutrinos. So these are the modifications, but now within this framework, all that we've measured in experiment, so not the dark matter problem, not the baryon asymmetry, we do not solve fine-tuning problems, but all the measurements conducted by humanity on Earth have an explanation in this framework. Now, this is a low-energy effective theory. Low-energy effective theory means that there are heavy degrees of freedom. Heavy is here much heavier than the electroweak scale, and they are not playing a dynamical role in the processes that we measure because they are too heavy, and their effects come into expression via the non-normalizable terms of the standard model. And the cutoff scale is roughly the mass scale of these new degrees of freedom. Now, if we have a certain low energy effective theory, usually there are several possibilities as to the full high energy theory that includes these heavy degrees of freedom in it that can produce the low energy. So to know which of these sources we have to produce directly, usually the heavy particles. As long as we do not do it, we have several options as to what is really the physics at the high scale. What kind of degrees of freedom are there that gave us the non-normalizable terms whose effect we did measure. So here I now will present the simplest full model. It's called full high energy theory. It's sometimes called UV completion, ultraviolet completion. This means completion at high scale. That gives as an effective low energy theory the new SM. And I also mentioned that this is perhaps the simplest, but not the only framework. And there are at least 2 more that produce the same new SM as the one that I will now describe. So I call that the NSM, and we see why. So I define it, extract the Lagrangian, the spectrum, the interactions, and argue that the low energy limit of that is the new SM. Let me say there is a rigorous mathematical procedure called integrating out. If you have heavy degrees of freedom that are much heavier than the energy scales in which you are interested, then you integrate out these degrees of freedom. It's a procedure by which you are left only with the non-normalizable terms and the effect of the heavy degrees of freedom, but the heavy degrees of freedom do not appear there anymore. So moving from a full high energy theory to an effective low energy theory is a well-defined process. So it's not a question of guessing. So here's the definition. Same gauge group, local symmetry as the standard model, same scalar content, same spontaneous symmetry breaking, and the only difference is in the fermion content, where I now add 3 copies of right-handed fermions that are singlets of SU3 color, singlets of SU2 left, and carry no hypercharge. So they are singlets of the complete standard model gauge group. So that's the modification to the standard model or its extension. So since I did not change the symmetry, all terms that were allowed in the standard model are allowed also here. So all the terms that do not include these new fields are still there. All the fields are in this model. The symmetry is the same. And so I now write a renormalizable model. So part of it is the standard model, renormalizable Lagrangian. And we only have to ask what kind of additional terms that involve these n fields we can add. So first of all, okay, so let me write and then I'll go. So there are Majorana mass terms for the new degrees of freedom. There are Yukawa, and there is, of course, the kinetic terms. So since they are singlets of the gauge group, then the covariant derivative is the same as the space-time derivative. Okay? They do not transform under any of the local symmetry. We don't have to compensate for that by coupling them to the gauge boson. So that's why it's written here d mu rather than, so del mu rather than d mu. Space-time derivative and covariant derivative are the same for these fields because they are singlets of everything. Second, they carry no charge. They do not transform under any of the imposed symmetries. And that's the situation where the Majorana mass terms are allowed. So every allowed term we should write. And so this is the Majorana mass matrix for this. It's a 3x3 complex matrix of mass terms. And for Majorana masses, such matrices are always symmetric because it's not psi left bar, psi right. It's the same field. So, yeah, symmetric. While the Yukawa that are now possible, left-handed lepton doublets and this thing, and the quantum numbers here are of phi dagger, general 3x3 complex of dimensional coupling. So these are the additional terms, kinetic, Majorana mass terms, and Yukawas, which were not there before. So what is the spectrum? So now we have a 6x6 neutrino mass matrix, a mass matrix for all the fields that are singlets in Q of SU3 color and carry no electromagnetic charge. Right? All of these fields, fermions, that do not transform under the exact SU3 cross U1 symmetry. There are 6 such degrees of freedom. The 3 knee left, the upper component of the left-handed lepton doublets of the standard model. And now we have also the 3 and right. All of them are singlets of SU3 color, no electromagnetic charge, and there are 6 such degrees of freedom. There is a 3x3 matrix for NRI, NRJ, and there is the Dirac mass matrix coming from the Yukawas when replacing the phi field with its vacuum expectation value. This is this MD. This MD is the mass matrix coming from the spontaneous symmetry breaking and the Yukawa. So there are 6 neutrino mass eigenstates. This has to do with their Majorana nature. For the charged fermions, all of them are Dirac fermions because they are charged, so by definition they cannot be Majorana particles. And 3 Dirac mass eigenstates have 12 degrees of freedom. For the neutrinos we also have 12 degrees of freedom, but the Majorana has 2 degrees of freedom. So there are 6 of these, 3 of these, but it's the same number of degrees of freedom in each sector now. So what does this matrix imply?
You see, there is a question online.
Yes.
So the question is from Debabrata Sahu. Do we need to add 3 copies of NR or we add less? We can add less.
Yeah, so we need at least 2. Okay, so if we have 1, okay, I did not, we would have, we want to explain the light neutrino masses. If we had 1, then 1 of the light neutrinos would get mass and 2 will remain massless. If we have 2, then 2 light neutrinos would get masses and 1 would remain, would get masses and 1 would remain massless. This is a possibility, so this gives a prediction that the light neutrino masses are hierarchical, that the lightest is massless, and we know then the masses of the other are the square root of delta m squared because one thing there is massless. So this model has prediction. With 3 or more, all 3 light neutrinos get masses. So in a sense, 3 is the most general thing for the low energy phenomenology. A larger number would not make a difference. A larger number of this, what would be heavy neutrinos, in a minute we'll see that. So we could have 2. That's a model with further predictions about the neutrino spectrum. 3 is the most general possibility to give all of them masses, all the light neutrino masses. So let's look for simplicity first. If there were only 1 generation of a lepton doublet and a single N left and a single N right, then the mass matrix would be like that, 2 by 2, MD left diagonal, MN here. And the mass eigenstates, you need to transform this into a diagonal matrix. And the thing here is that we will assume, that's not part of the model, but that's what of interest to us, that this mass scale, that we don't know a priori what it is much larger than the electroweak scale. So this is a parameter of the theory, a dimension full. In the renormalizable standard model, we had 1 dimension full parameter. Here we have more, all the entries in the MN matrix. With 1 generation, it's 1 new dimension full parameter. And for the sake of good phenomenology, we assume that it's much larger than V. In this case, to leading order in V over Mn, we have 1 heavy state with mass that is at leading order Mn, and 1 light state with a mass that is Md squared over Mn. And a simple way to see that this is the case is that when you diagonalize such a matrix, the determinant and the trace are not changed. So the trace is Mn, and to leading order, these 2 masses are, this is very small, so to leading order, it's Mn. And the determinant is Md squared of this matrix. And the determinant of the diagonal mass matrix, Md squared over Mn times Mn, is Md squared. So these are the 2 eigenvalues to leading order each in V over Mn. And the diagonalizing matrix, cosine theta, sinus theta, minus sinus theta, cosine theta, this rotation angle is also small. It's md over mn, once we assume this hierarchy. And so, in this model, we have really three scales. The scale of the light neutrino, the electroweak scale, and Mn. By assumption, this is much larger than that, and by the same assumption, this is much lighter than this scale. And moreover, the larger Mn, the smaller the mass of the light neutrino. And so this is the reason that this model is called the seesaw mechanism. You have two neutrinos sitting on a seesaw, the heavier one of them, the other one, well, it goes reverse seesaw. The other one becomes lighter. Moreover, this mixing angle is the transformation for the basis where you have a neutrino that came from a doublet and a neutrino that came from a singlet of SU2. And if the mixing angle is small, it means that the light state is almost purely coming from the doublet, and the heavy state is almost purely coming from the singlet, up to deviations that are of order md over mn. So this is the component of the doublet in the heavy state, and it's the component roughly of the singlet in the light state. I hope I don't confuse you too much. So that's with one generation, and the extension to three generation is kind of straightforward. It's a bit more complicated, but this is the spectrum of this model under the assumption that all, if you want, the eigenvalues of the Mn matrix are all much heavier than the scale, the electroweak breaking scale. So there are three heavy Majorana neutrinos. We call them N1, N2, N3, of masses M1, M2, and 3. They are very close to being with well-defined transformation property under SU2, being the singlets, but they have a small component of a doublet. There are three light Majorana neutrinos, Ni1, Ni2, Ni3, masses M1, M2, M3, of order V squared over Mn, and they are approximately doublets, but have a small component of a singlet. And so the model has three mass scales. Unlike the renormalizable standard model, it has one, V. Here there are, so in the standard model, all massive particles, their masses are of order V. Here there are the scale Mn, where there are singlet fermions, singlet neutrinos, singlet of SU3 color cross U1 electromagnetism, all charge fermions, and the W, and the Z, and the Higgs have a mass of order V, and there are three very light neutrinos with mass of order V squared over Mn. Okay. Interactions. So that's the spectrum. Okay. Three very heavy neutrinos, three very light neutrinos, and all the charge fermions and massive bosons in between. The neutrinos, both the heavy and the light, carry no SU3 color, so they don't couple to the gluon, no electromagnetic charge, so they're not coupled to the photon, and there is no anything new about the strong and electromagnetic interactions, while all the others are modified. So the charge current, this is okay, a bit advanced, but we have still three charged lepton mass eigenstates, E, mu, and tau. The thing that transform as a singlet of SU3 color and charge -1 under U1 electromagnetism. There are three such states still. But there are 6 states which are singlets of SU3 color and neutral under U1 electromagnetism. And so the W interactions connect between these 3 charged mass eigenstates and the 6 neutral mass eigenstates. If there was not the small component of a doublet in the heavy neutrinos, we would not have this thing here that connects the charged leptons to the heavy states. But these are the mass eigenstates, and they do have a small component of a doublet to which the W does couple. So the W couples to the small component of a doublet within this heavy mass eigenstate. But the thing here is that the mixing matrices are between mass eigenstates, and so we have 3 charged lepton, 6 neutrinos, and the mixing matrix is 3 by 6. And yeah, this is the notation. And in this part, okay, 3 by 6, in this part of the matrix, 3 by 3, all entries are very small. They're just of the size V over Mn, which tells us the size of how much a thing coming from a doublet is in the heavy mass eigenstate. And since these are very heavy, we will not be able to measure this part in experiment, in these models. But similar to the NUSM, the charge-Kern-weak interactions are neither universal nor diagonal. There is a mixing matrix. Also in the coupling of the charged leptons to the light neutrinos. I will not go into the Z interactions, even though they demonstrate something that I said, so maybe I just mentioned that. So I said that it's a special feature of the standard model that the Z interactions are universal. Unlike the photon and the gluon, which correspond to exact gauge symmetries and therefore must be universal, the Z I said had to do with a special feature that in the standard model, the renormalizable standard model, all states of a given SU3 cos U1, SU3 color cos U1 electromagnetism transformation come from the same SU2 cos U1 representation. If that's not the case, then the Z couplings will not be universal. This model is an example of a model where this feature of the standard model does not hold. Not all the particles with the same SU3 color cos U1 electromagnetism quantum numbers, or specifically those that are singlets of SU3 color and neutral under U1 electromagnetism, they come from 2 different SU2 cos U1 representation. 3 of them, these light things, come from doublets of SU2 with hypercharge -1/2, and 3 of them, the ends, come from singlets of SU2, singlets of U1 hypercharge. And in this case, the Z has off-diagonal couplings, and its couplings are not universal. The effects are small. They are of this order, the deviation from universality in the Z coupling to the light neutrinos, but they are there in principle. And it demonstrates that the standard model has this unique feature that it may be lost when we extend it. Okay, I will not go into details about the Higgs-Yukawa. It's now, as for the first time, we see off-diagonal Yukawa couplings in this model. And I said also that this proportional diagonality of the Higgs coupling is again related to unique features of the standard model, and these unique features are violated here, but I will not, too complicated for now. So just a word about the heavy states. We will not produce them probably in experiment. Their mass scale is likely to be at the 10 to the 15 GeV or so. So we will not be able to probe their properties in experiment, even though it would have been very interesting if this model is indeed realized in nature. But there is one implication that is very interesting. So the Ni particles, these heavy mass eigenstates, they are not stable. There is no symmetry that protects them from decay. And they decay to a light lepton, either a neutrino or a charged lepton. and a boson. And the boson is either the Higgs, which now has off-diagonal couplings, including to the heavy and light, the Z, which also couples to heavy and light, and the W, we saw before the 3 by 6, it means that it also connects this right part of the matrix, connects the heavy mass eigenstates to the charged leptons via the coupling to W. So it can have decays either to a neutrino and a Z, or to a neutrino and Higgs, or to a charged lepton and a W. These are the decay modes. And so as I said, by assumption they are very heavy, cannot be directly probed. But these decays turn out could account for the baryon asymmetry of the universe. There are here new CP violating phases in Yukawa and in other parts in the mixing matrix. And actually, since this model is a full model that explains neutrino masses, it was invented for that purpose. And then for free, you get a very nice possible explanation of how the baryon asymmetry was generated. Then this is a very popular idea now, a very shared by a large part of the community, that it's plausible that actually this is the way that the baryon asymmetry is generated. This is called leptogenesis. So it means that first you create an asymmetry in the universe between the number of leptons and anti-leptons, and then there is a standard model mechanism that perhaps in the next hour I'll mention, that converts part of this lepton asymmetry into baryon asymmetry. One can do detailed calculations of how this happened depending on the parameters of this model, and you don't need any particularly large number or small numbers. Numbers of order 1 of the new parameters are very nicely can account for the size of the observed baryon asymmetry. Okay, so these N fields are very heavy. I said that there is a well-defined procedure of integrating them out and getting a low-energy effective theory. If you look in the slides, there is here a pictorial explanation of how the dimension 5 of the effective theory come from renormalizable terms in this full theory. I will not go into that. I'll just say that if you integrate out the degrees of freedom of the 3 heavy neutrinos, you get the standard model as an effective field theory. You get at dimension 5 the terms of the newest M, LL phi phi, and you get also dimension 6 and higher that involve leptons, but they are at present not relevant to phenomenology. So this could be a high energy theory that produces the dimension 5 terms that we have essentially, I think, measured in our experiment. But it's not the only possible high energy theory that produces the newest M at 3 level. This is, I mean, if not at 3 level, there are even more. So this is called type 1 CISO, this NSM model. It's adding to the standard model's list of fermions, fields that are singlets of the gauge group. That's what we've done now. Type 3 CISO is also adding fermion fields, but they are singlets of SU3 color, triplets of SU2 left, 0 hypercharge, so it's different representation from that. But at low energy, the dimension 5 terms are the same. And an even more perhaps surprising source, you can add no fermions, add just scalar fields that are singlets of SU3 color, triplets of SU2 left, hypercharge -1. Again, give them a mass scale that is very high, this mu squared, this dagger times itself, this mu squared you put at a high scale, you integrate them out, and you get the same dimension 5 terms. So that's called type 2 CISO. So there are at least 3 frameworks that give the same dimension 5 terms, which says that as long as we did not have a direct access to the heavy fields, we cannot know. So neutrino masses don't tell us if the theory of nature is this, or that, or that, or perhaps something that creates it at the loop level and not a tree. To the best of our understanding, it does tell us that we've seen the dimension 5 terms of the non-normalizable standard model, of the standard model as an effective field theory. Open questions. So first of all, this new SM is a very plausible extension of the standard model. Experiments established that neutrino have masses and mix, as predicted by the new SM. They determined 5 of the parameters out of the extra 9. Yet to be answered by experiment is whether the neutrino spectrum is hierarchical or quasi-degenerate. So these are the 360 degrees, and here is the chalk. So it's this. So this is the mass of the neutrinos. And it could be, here is 0. It could be that one of them is massless, and yeah, and the other one, for example, is here, and the third one is here. That is called hierarchical. It could be that they are well above here, somewhere. Yeah, so this is at least, so in this case, this is 0.009 roughly EV. And this is 0.05 EV. And that's hierarchical, okay? It could be that they're all much heavier because all we know is the mass square difference. So it could be that they are somewhere here, in which case they are really very close to each other, okay? If they are heavy but have the same mass square difference, they must be almost degenerate. You can do the calculations and see. So we don't know if it's this case or this. This is hierarchical, and this is quasi-degenerate, and it could be anywhere. This, what we know is that this is not heavier than the EV scale, okay? 20 times larger than that, roughly. So that's the first question. The second is the neutrino mass ordering normal or inverted. So this is what's called normal. Inverted, I put these two here and the massless one here. Or here I put the smaller mass splitting above and this one below. And again, going from here to here over the whole range is a possibility. So we don't know. I don't exactly know why this is called normal and this is considered abnormal, but that's, you know, I think I know actually. This would be very surprising because this means, also this means that there is degeneracy in nature. So that there mass, at least two or maybe all three are very close to each other without a basic explanation. This would be a surprise. We do not see really degeneracy in the charged fermions. So we expect it to be hierarchical perhaps, but that's a naive theorist expectation. We do not yet know whether CP is violated by the lepton mixing matrix. It's hard to believe that it's not, okay? CP is violated in nature. It has the freedom of having it in the leptonic mixing matrix. There is no reason whatsoever that it will not be there. There is no symmetry that can forbid that. But again, we want to see it experimentally. So we want to know if the neutrinos are Dirac or Majorana fermions experimentally. We want to know if there are additional light neutral fermions. These are called sterile fermions. The newest M says no. Only the known neutrinos are light. And we want to know if dimension 6 terms are also important for lepton flavor violation or lepton number violation. So far, we've seen only the effect of dimension 5. I believe that the newest M is realized in nature, but we would like to know what is the full model, what are the new degrees of freedom that generate it. And all of this is part of a rich and exciting experimental neutrino physics program that is going around the world, and some people here are involved. And as I said, neutrinos have surprised us so far many times, even by their very existence. That was first understood because it seemed that there are processes that do not conserve energy, which was a complete surprise. And at that time, early 30s, suggesting new particles that have not been observed or giving up on energy conservation were thought to be equivalent or similarly revolutionary. Nowadays, theorists invent new particles as they wish, as many, they go crazy with it, and no one would think that energy conservation should be given up. But in the early 30s, it was a very daring thing by a theorist, in this case Pauli, to suggest that instead of violating energy conservation, there are particles that the detectors cannot get. Actually, I don't know if you know, it's a very famous story because he suggested it in a letter to conference participants. He apologized that he could not participate in the conference because he is invited to a party. I don't think that nowadays any serious physicist would dare to say that they are giving up on a conference because they go to a party. I'm not sure that there are many physicists that would prefer a party over a conference, but that's the case. And then he also kind of apologized for suggesting this crazy idea that there are particles in nature that we cannot see. And actually, he thought that we will never see them. So, which in, I think, 2 decades, the neutrinos were observed and proved to exist. So that was their first appearance on physics, on particle physics, and since then, they have masses, they make strange things to the sun, in the atmosphere, etc. So I think that's it for the neutrinos. Yeah, it's time to stop. So, thank you.
Questions?
So why these quasi-degenerate levels lie higher than the hierarchical levels?
Yeah, suppose you have a mass square difference, m2 squared minus m1 squared. You measure it, and now you can write it if you want as m2 plus m1 times m2 minus m1. And so in a sense, the heavier they are, the more they generate for a fixed delta m squared. The degeneracy is stronger for a fixed delta m squared. The heavier, if you want, their average, this is twice their average mass, goes up. They become closer and closer to keep the same delta m squared. So that's the reason. Yes.
So, can you go to the baryogenesis slide? Go back to it. Yeah. Just this one. So, these new particles can decay into light leptons, right? As we saw from the interaction term.
They can decay.
Decay into these light leptons, neutrinos and
Yes.
the charged leptons, but they can also decay into the antiparticles, right?
Right.
So, like, is it because of the CP violation that is the reason for the baryon asymmetry?
Okay. I think I understand the question. So you will deduce from the answer whether I do. So the decay, let's say, to a neutrino plus something or to anti-neutrino plus something, that's a result of their Majorana nature. They do not, the mass eigenstate do not have a well-defined lepton number. They are, in a sense, the mass eigenstates are a mixture of what you call neutrino or antineutrino. So that's a result of that. If their decay to a neutrino plus a boson and to anti-neutrino plus a boson, it's the same boson, the Higgs or the Z, occur at different rates, that's the CP violation. Not the fact that it can decay to both, that's Majorana, that's lepton, that's exactly the manifestation of lepton number violation that comes from their Majorana nature, but a difference in rate, that's CP violation. Since the Yukawas are complex in general, the Yukawas of these heavy neutrinos in the light, then there are many phases in their Yukawa couplings, and that's why there can be CP violation, and it's calculable, okay? And if I get to baryogenesis in the next hour, we may even see the formula for that and understand roughly how it arises.
So this different rate of decay into particles and antiparticles will give rise to the asymmetry.
Yes, yes. There will be preference for producing, let's say, neutrinos over anti-neutrinos in the universe, yes.
So, the baryon asymmetry. So the operator dimension 5. I can generate the baryon asymmetry in dimension 5 or dimension.
Sorry, but I did not understand the question.
So
And
the
slowly
effective
for me.
field operator dimension 5.
And-
I can
and-
generate baryon asymmetry
No,
in
no,
dimension
so-
5.
So the baryon asymmetry, to understand it in this scenario, you need to include your heavy degrees of freedom n in the model. The effective dimension 5 by themselves cannot account for the baryon asymmetry. It comes from the decays of this n. So you have to have the scenario of creating the baryon asymmetry this way. The model must include the particles that decay, which are these heavy ones. In the dimension 5 terms, you don't have them. So there you would not, by this you will not see that leptogenesis can happen. You need the full high energy model.
There is an online question. Debabrata Sahu is asking, what is the present status of neutrinoless double beta decay?
Upper bounds,
He just asked this, yeah.
yeah, I didn't explain exactly what they measure. They measure something called MEE. This is a combination of neutrino parameters. It's M1 UE1 squared plus M2 UE2 squared plus M3 UE3 squared. And it's not absolute value of UE1. So that's, you see also how Majorana phases play a role. And M1, M2, M3 are Majorana masses, so this has in it lepton number violation. And they put an upper bound on this, which I don't remember exactly what it is. It's below EV, but still well above 0.05 electron volt. I don't think they can get to 0.05 electron volt. And so I know that it's in between because if neutrinos are hierarchical, then the experiments don't have enough sensitivity. So these are small numbers, M1, M2, 3 in this sense. And then it seems that the experiments, the current technology cannot get to such small values. If they are in such a region, so M1, M2, and M3 are larger, so if they are quasi-degenerate, if they are well above 0.05 electron volt, then very likely at some point the experiments will see the effect. I have to perhaps mention that seeing the effect or seeing the process of neutrinoless double beta decay would be unambiguous signal of lepton number violation, and except for some caveats, a proof that the neutrinos are Majorana particles. But the translation of what is measured by this experiment, so the rate of the process that they will extract into this parameter, has uncertainty. So we will know that it's there, but the exact value has some nuclear matrix elements in it, which we do not have a precise knowledge of it. So qualitatively, it will be revolutionary to see it. Quantitatively, there will be large uncertainty in the translation into this parameter of the newest M. Yes.
So these heavy neutrinos, how heavy are they? I mean, do we
How-
have
how heavy?
idea of the masses? I mean,
Okay, so that's so the light neutrinos are of the order of, say, some Yukawa squared, v squared over the heavy mass. What we know is that this combination is, let's say, of order 0.05 electron volt, order of. If this is of order 1, then Mn is of order 10 to the 15 GeV, right? We know what V is, so. So if it's above 1, then the theory is perhaps non-perturbative. We want a perturbative theory, so that's why this is an upper bound. It could be that Yn is smaller than 1, and then Mn will be something like 10 to the 15 GeV times Yn squared. So the smaller Yn, the lower the mass scale of these particles. We don't know what Yn is, so that's why this is an upper bound. Assuming that Yn is not crazily small, at least for one of, let's say, third generation, I don't know, let's say perhaps at least 10 to the minus 2, then the scale would be at least 10 to the 11 GeV. Still far above the electroweak scale.
and if they're decaying to say Higgs decay to Higgs boson.
They can decay. One of their decay modes of the heavy ones would be
Yes.
to Higgs and neutrino.
And is it through some loop, leptonic loop?
No, it's so,
Simple.
yeah, so
Okay. Okay.
yeah, so these are the Yukawa. The Yukawas are
Okay.
essentially Yn, but since we want the mass eigenstates, then it's multiplied by this unitary matrix that takes you from the neutrino mass eigenstates to from the interaction eigenstates to the mass eigenstates. But the Yukawa is this Yukawa more or less in the Lagrangian. So it's this.
Okay.
Yeah.
And then can we, essentially the Higgs mechanism and the mass generation, can we relate to it in some sense?
So the Higgs is responsible, the Higgs mechanism
Yeah.
is responsible to this MD up there.
Okay.
This is the Yukawa times the vacuum expectation value, these entries here.
Okay, okay.
For charge fermions, there is no Mn, and then Md is the Dirac mass matrix, etc. Here, because there is also this ingredient that the singlet things have a Majorana mass, then this is not the mass, but the eigenvalue is Md squared over Mn. Okay, but the Higgs mechanism is here. These are Majorana mass terms
Okay.
that are allowed already in the Lagrangian because the N fields are singlets of the imposed symmetry group, SU3 cross SU2 cross U1. So you have these terms in the Lagrangian. This comes from the Higgs mechanism. These have nothing to do with the Higgs. It's what we call L psi. This comes from L Yukawa. This comes from
So
L psi.
Majorana nature is basically preserves the symmetry SU2 cross U1. It doesn't spontaneously breaks. Can I say this?
Right. These Majorana masses do not break any symmetry.
Okay, don't
It's
break
only
any
allowed because these are complete singlets of SU3 cross SU2 cross U1.
Okay.
Yes.
Okay.
Okay, now maybe we break for the tea afterwards.
Let's.
Because the tea break is,
So the tea is
we
getting
need to,
colder.
because
or-
online participants will join at 11:30. We can take up the questions at the end of the
But
next.
you should remember your questions, right? There were
Yeah,
at
you
least
should
two
remember,
fingers here.
write down your questions.
Yeah. Let them not be
So we have
forgotten
only
in the
10
tea.
minutes for the tea break. Yeah.
And these are still neutrino related questions, right? So I will leave neutrino related.
So yeah, we can have the questions. So you had a question and then we have something online as well.
Hello. Yes. So, sir, I wanted to ask that the whether the neutrino have the normal ordering or inverted ordering, it is still a question. So there have been recently several papers which has claimed that the normal ordering are preferred more. So how can we say that the normal ordering is preferred over the inverted ordering? How can we say that experimentally or even as a theoretically?
Yes, so I vaguely remember the answer. That's the experiment, okay? I think Dune and other experiments should be able to tell us. So we know that we can now distinguish between the 2 and the 1 by the mixing angles that they have. Let's see. That's already in the new SM. Lost it. Here. Okay, so we've measured the mixing angles, let's say the electron component in 1, which is the lighter of the two, and 2. Yeah, so first of all, UE2 is about 0.58, and UE1 is, I think, square root of, 2 over square root of 6, I think. Yeah, 2 over square root of 6. So one of them is larger than the other. So I think this one is larger than this one. And so you see here a definition. In the lighter one, the component of the electron neutrino is larger than the component than in the heavier of the two. So we have a definition via the mixing. We know features of what does it mean 1 and 2. So we also know, so in 1 and 2, we know it. Here, we know that the electron component in the one that is separated is very small compared to the other two. Now, if it's heavier or lighter, it has an effect on the measurement of neutrino oscillations that has not been, this is a small effect, has not been observed so far. And I have to admit, I don't remember exactly how, but these more precise neutrino oscillation experiments are sensitive to also delta m squared E3. To 3, perhaps someone in the audience remembers better than me, but there is this dependence. The fact that we know this is because the sign of delta m squared 2-1 is because in the solar neutrinos, it's not vacuum oscillations, but MSW effect. And so if going through matter, then the sign is known. Now, I don't remember if, for example, Dune will be able to fix it because there is an effect of the matter between the source of the detector or because of other reason, but the result there of their measurement of neutrino oscillations will depend on whether delta m squared 3, one is positive or negative, which is what we call the ordering, normal ordering. For the absolute mass scale, I think we will need either experiment like Catherine, which is sensitive just to the mass to find the signal, or for neutrinoless doppel decay to find the signal. Otherwise, I think it's harder than, so the hierarchy of quasi-degeneracy, I think, is more difficult experimentally than the ordering, and I think the ordering is expected to come out together with the CP violating phase from experiments like Dune.
And sir, my other question is that yesterday.
Does it work, the microphone?
Yeah.
Okay. Good.
Yeah. So my other question is that yesterday you were talking about the some condition of universality and diagonality, and you were also talking about the search for the new physics. So how these? So I don't understand how both of them are related to each other.
Okay. So universality, instead of the electromagnetic and strong interactions, is kind of guaranteed in theory, and while it's still interesting to see in experiment that it works, but it's much more interesting to test universality, for example, in Z decays. So practically, you would measure as well as you can, let's say, Z decay to U plus U minus, E plus E minus, tau plus tau minus. I now focus on the leptons because it's a little bit easier experimentally, and see if there are differences. Diagonality, it's searching for modes that are not observed at all, like Z going to E plus mu minus, or Z going to tau plus mu minus. In the theory, each of these, if violated, so if we see non-universality, the diagonal modes have different rates from each other, or non-diagonality, the Z decay to two different flavors, it would hint at the same violation of a feature of the standard model. It will tell us that in this sector, particles that have the same color and same electromagnetic charge come from different representations of SU3 cos SU2 cos U1. In the fermions, it's usually called the representations that can be added to the standard model and lead to that are called vector-like representations. So in the standard model, all representations are chiral, left and right hand different, everything is. If you have additional fermions that are left and right are in the same representation of SU3 cos SU2 cos U1, which does not happen in the standard model, then this will lead to such violation of universality and diagonality. So if we observe that, the straightforward interpretation is the existence of such vector-like quarks or leptons, depends where we see it, beyond the fermions of the standard model. So these are universality and diagonality in Z decays are in a sense two different directions to look for the same type of extension of the standard model. In the Higgs decays, it's not universality because the Higgs does not couple in the same strengths to tau, mu, and E. You look for deviation from proportionality to the masses, and you can look for off-diagonal couplings. Here, if you see either of these, the straightforward interpretation has two possibilities. One is that there is more than one Higgs doublet in nature, 2 or 3. That's one interpretation. And another is again that there are vector-like fermions beyond those of the standard model. Each of these extensions will lead to the violation of the proportionality and of the diagonality of the Higgs decays. So these are why we are looking for these. We want to learn of degrees of freedom that we did not observe in this indirect way by the properties of the particles that we do observe.
And sir, one more last question. We know that the delta m square 21 is greater than 0. Where does this comes from?
It comes from the solar neutrinos. So, as I said, the solar neutrinos that we observe above 1 MeV convert their identity not by vacuum oscillation, but by the MSW effect. So it's already happening in the sun. Actually, what is produced is electron neutrinos in the sun only, but what the MSW effect does is to make those neutrinos with electron neutrinos with energy higher than 1 MeV, it makes them neutrino 2. It projects them on the mass eigenstate. And if it's what comes out of the sun, already the surface of the sun is a mass eigenstate, then it doesn't oscillate on the way to Earth. So it's very different from vacuum oscillations, where the oscillations are on the way. Here, the conversion is inside the sun, and on the surface, it's already a mass eigenstate. And from the mechanism of MSW, we know that, okay, what the sun, since the, what we know is that the flux of electron neutrinos coming from the sun is a third of what is produced. So it tells us that UE2 squared is roughly 1/3, and that this 2 is the heavier of the two. So it tells us the component of electron neutrino in the heavier between these two states, the component squared is 1/3. So this is about, I think, 0.58 or something like that, which is needed. So it means that UE2 is of order 0.58. So the MSW effect tells you, if the MSW effect is the source of the fact that the flux that is detected here is different from the flux that is produced, then it tells you what's the component of the electron neutrino in the heavier eigenstate between the two. So that's how we know it. It's not vacuum oscillations, which are proportional to sinus squared delta m squared something, and if it's sinus squared, we don't know the sign of delta m squared from that, from vacuum oscillations. MSW, we know.
There was one online question, maybe we'll just quickly take that and then move on. There was no other question from this side, right?
There was, but it disappeared. I will not tell who raised her hand before, so.
Oscillated away. Yeah, here's the question. So again from Debabrata Sahu, why we do not accept that the neutrino has this small mass due to very small value of the Yukawa coupling, then we do not need to extend the model.
Okay, so there are two answers to that. First, it's not true that we do not have to extend the model in order to have a very small Yukawa, because a Yukawa for the neutrino requires these n fields. Yukawa couples, in order that the Yukawa will give a mass to the upper component of L, what's need to be here is exactly this field n that transforms like 1, 1, 0. So for the neutrino to get a mass from Yukawa coupling, it's only possible if we have such a field that we introduced. If we introduce this field for the Yukawa, in general, it will have a Majorana mass term and will go to things that I introduced. The other way is to say that I want to have only Dirac mass, small Yukawa, I have to forbid the Majorana mass term. So since it's not forbidden by any of the imposed symmetries that I did, the only option more or less is to impose lepton number. This is a much more dramatic extension to my mind of the standard model. Not only you introduce new degrees of freedom, you also impose a new symmetry that was not there in the standard model, whereas this is a global symmetry, which we do not like, and whereas we have to assume that the Yukawa, we have here, for no special reason, Yukawas that are all of order 10 to the minus 12 or smaller, much smaller than all the Yukawas of the standard model, and we don't have a natural explanation of why the neutrinos are light. If you introduce these anyway, because you must for both scenarios, write down without imposing an NS symmetry all the terms that are allowed. Just say that there is a new high scale in physics related to the masses of this, and then there are Majorana particles, and you understand why they are light, and you don't have to impose any extra symmetry. So it's possible to do it, but it's not true that you do not have to extend the model in order to have Dirac masses for neutrinos. You must extend both the particle content and the symmetry, and by imposing a global symmetry. So I doubt that that's what's happening in nature. Okay, so let's see a little bit about particle cosmology. Given the time, it will be very little. So, why do particle physicists and cosmologists talk to each other, except for curiosity? There are good reasons we talk. So, why does cosmology needs an input from particle physics? Because in the very early universe, the entities that were roaming around in the universe were not human beings and not galaxies and not clusters. It was the elementary particles. Okay? The very, very early universe was a soup made out of elementary particles. The distances between them were very short. Temperatures were very high, so very high energies. And so to understand what's going on, you need particle physics. Particles, their interactions, etc. So, yeah, it's crucial. Then you need nuclear physicists for later times, then atomic physicists or whatever, but in the very beginning, particle physics is crucial. Why is cosmology relevant to particle physics? This is a question that I think to me is fascinating, because the universe provides us with an experiment, a very interesting experiment, because it gives us conditions, very, very high energies, very short distances that we cannot produce in our experiments. And we all suspect that at some high energy scale or mass scale, there are new degrees of freedom, and it's not unlikely that at very short distances, there are interactions mediated by force mediators that are much heavier than the W in the Z, so the range is very short. And cosmology that along the history has been probing these conditions, this high energy, might reveal to us the things that we are missing, might reveal to us new degrees of freedom, or a particular show where the standard model cannot explain things, and cosmology requires new ingredients to the standard model. This experiment is, however, difficult for us for two reasons at least. One is that it's, as far as we know, or hope even, it's a one-time experiment. We have a single set, so we don't have statistics, right? There may be many universes. I think according to common wisdom in string theory, there are 10 to the 500 universes or so, and we live in one of them, but we have no access to the other. Now compare it, for example, to the LHC, not the high luminosity, but the current one. The LHC has proton-proton collision every 25 nanoseconds, which means 40 million repetitions of the experiment per second, multiplied by the number of seconds per year. In physics, by the way, in reality, it's about 3 times 10 to the 7, but physicists, it's 10 to the 7, because part of the time the accelerator is not working. So 10 to the 7 seconds a year times 40 million repetitions per second times some 30 years for which the LHC will function in its... it's many times, okay? We have statistics, huge statistics, right? It's a statistic, I don't even guess it's about 10 to the 40 repetitions of the proton-proton collision. While here, it's one time, and we cannot do statistics. And the second, which is even more intriguing, is that we did not prepare this experiment, okay? So when we do accelerator experiment, we build the experiment, we know exactly the proton come with a center of mass energy of 13 TeV, they collided here. We know the initial condition, and we measure the final result in our detector. For the universe, we measure the current results, in what we can observe, but we did not, it's not us that have designed and built this universe. And so if there is a dependence on initial conditions, we might be in trouble. So how can we do anything with cosmology? First of all, sometimes the current universe does not depend, features do not depend on the initial conditions. Anything that has been in thermal equilibrium along the history of the universe, thermal equilibrium, initial conditions are erased, they do not matter anymore. And actually, to our understanding, all the standard model particles have been in thermal equilibrium at some point in the history of the universe. So, for example, their abundances at current time, we know how to calculate that, independent of initial condition. Second, if there has been inflation, that also frees us from initial condition. And third, sometimes even things change, we know more or less how to calculate backwards what has happened with them. And fourth, this is the thing that personally I like most, you must assume for cosmology simple initial conditions. Now it sounds like something arbitrary. Why should have the universe begun in a simple way? And the answer is that if it did not, then we are lost. And the example of that is that if the universe starts not from simple initial conditions, it could have started 10 minutes ago. Now I know it sounds bizarre because all of us believe that we've been sitting here at tea break 10 minutes ago, but it could be, right, that it started with very complicated initial conditions where each of us human beings have implements memories that are longer, and we think that we understand the history of the universe, but that's complicated initial conditions, okay? That's take someone, a big expert in computer games, to program us in this way, but maybe there is one. So it's crucial that there are simple initial conditions, and that makes, and if you assume that, then you can do cosmology, right? If it started 10 minutes ago, then there is no Big Bang or anything, it's just an illusion. Perhaps more, okay, so if someone designed the universe that with the illusion that there has been a Big Bang, etc., so let's play her game and assume it's also and investigate it. But it means that there is not an infinite list of things that we can observe and get lessons from them from particle physics. I think these are the big four, at least for me. Perhaps also you can add dark matter to that, but dark matter for me is mainly astrophysics. Okay, so the cosmic microwave background is something that, it's a picture of the universe, okay, a photo of the universe, 380,000 years after the Big Bang. At that time, the temperature dropped enough that electrons could combine with protons and create neutral hydrogen atoms, which are transparent to light. So until then, light all the time scattered because electrons and protons did not bind, or they bound immediately, were unbounded by hitting photons. And then suddenly the universe became transparent, and the photons that were there are free to travel since then until now and give us this nice picture of the universe at that age. Large-scale structure, why there are galaxies, I thought it's highly actually counterintuitive that we have large-scale structure, because I would expect the universe to be on either of two extremes, sorry for my naivety. Either it's a kind of a unified or same soup everywhere of particles or whatever structure that you want, or somehow gravity would bring everything massive to one place and we'll have a big chunk of matter. But it's neither of these extremes. We have typical scales. We have clusters of galaxies, planets. There are scales in the universe. This is the large-scale structure, very rich source of information. That's a long process, but roughly, depends on whom you ask. Let's say something about the conditions at the universe 10 to the 5 years. But we want to get closer. Big Bang nucleosynthesis, essentially the abundances of 4 light elements, hydrogen, helium, lithium, helium-3 and deuterium, was determined at processes that started at 1 second and ended at 3 minutes. And so this is a window to universe when it was, let's say, 1 minute old. Not bad, we're getting closer. And the baryon symmetry of the universe, the processes that led to it, we know for sure, almost for sure, ended up at latest when the universe was 10 to the minus 11 second old. And that's a window to a very early universe. Now, taking into account that our experiments produce energies, okay, hundreds of GeV, TeV, which was about the temperature. The temperature is the typical, up to a factor, the average energy of the photons at the universe at that time. So we get as high as the energies at that time, 10 to the minus 11 second. Then the temperature was around 100 GeV. Then if we get windows to earlier times, we get test of the standard model in conditions where it has not yet been tested in our laboratory. So that's particularly interesting, and perhaps we should not be so surprised if here is where we find inconsistencies with the standard model, because we have an hypothesis, the standard model, or if you want GATT or supersymmetry or whatever, but we did not test it experimentally, and the universe is an experiment that allows for that. So dark matter is somewhere between particle cosmology and astrophysics. So let me go rather quickly. So what is dark matter? Massive particles that are stable or have lifetime much longer than the age of the universe, in order they are still with us, and interacting weakly or not interacting at all with the standard model particles, but in particular do not have electromagnetic and color interactions, or else it would not have been dark. You would have seen them. And the first proof came from the galaxy rotation curves. So if all the matter in a galaxy, or the bulk of the matter, is up to some radius from its center, then stars that are further away from this bulk of matter should have their velocities go down along this curve. Instead, they approach constant thing, and that means that there should be additional matter here that we do not see, up to much larger radius than the one where the bulk of the galaxy or the luminous matter is there. So that were the first indications of dark matter. The big astronomy step in proving them was by astronomer Vera Rubin, who perhaps did not get enough recognition at the time. She just measured this very, very accurately, unprecedentedly accurately, and I think, sorry for two gender-related sentences, she refused to put in her papers the words dark matter. She said, I'm an observer, I measure rotation curves of galaxies, this is what I will report. I doubt there will be many male astronomers showing this constant curve that would not say in the papers, this may hint that there is dark matter in the universe, right? Because that's the exotic part of that. Anyway, she now got the big new telescope, Vera Rubin telescope, called after her in recognition of her achievement. Second, gravitational lensing and the bullet cluster. So the bullet cluster is actually two clusters that have collided. They are going through each other. And we see these points of light are galaxies in these clusters. We see them in optical imaging. We see the hot gas that's still baryonic matter, something that shines. We see it in pink. And through gravitational lensing, we have a measurement of the mass that is there. And we see that the mass is very well extended beyond the luminous thing. So there are things that pass each other with little interaction and they do not shine. And there is the baryonic matter that the interaction kind of keeps it more in the middle. And so that's really, seeing it in three ways tells us that there is massive matter which is not just luminous. It's a picture of that, if you want. It's almost a picture of dark matter, even though this is kind of a paradoxical term, oxymoron, but in the sense that we see it through gravitation. cosmic microwave background tells us that not just that there is dark matter, but it consists about 26% of the energy density of the universe, while the luminous matter, the baryonic matter, gives about 5%. That's it. So the standard model, I think, perhaps more than speculating on what it is, the most interesting thing is that the standard model doesn't have the dark matter, even though it has dark matter. Okay, so it has neutrinos, and neutrinos carry neither color nor electromagnetic charge, and they are stable on the cosmological scale. According to the standard model, they are completely stable. If you go to the newest M, they are not completely stable, except for the lightest one, but you can see that their decay time is much longer than the age of the universe. So they are dark matter. Could they be the dark matter? And the answer is no, no, no. I think that I counted right. 3 reasons at least why they are not. So first is, I told you that anything that has been in thermal equilibrium, we can tell how much there is of it in the universe. Same for neutrinos. We can calculate. I will not go into it. Just tell you that we are in the universe. There are about 110 neutrinos in centimeter cube of the universe, and that it's much less than, oh, it's not much less, 3/11 than the number density of photons, much more than the number of baryons. And from this we can calculate the contribution. It's the sum of masses over 43. And okay, 1 eV is that they are very at the highest scale, but if it's 0.05 electron volts, 20 times smaller, then at most 1% of the dark matter. And so probably only a small component. They cannot be the dark matter. Second, from the large-scale structure, we know that most dark matter particles should be cold. Cold means non-relativistic at the time of the structure formation, namely that their mass should have been heavier than the temperature at that time. Neutrinos are hot dark matter. The large-scale structure would have looked different in the universe if dark matter were neutrinos, so that's the second no. The third no is a bit more complicated, but there is dark matter in our galaxy, and in order that it will be bound to the galaxy, it should have a mass of at least 70 electron volt. The more massive it is, the less density there is, and or if you want, the lighter it is, the more density, but there is the exclusion principle of Pauli, and so for fermions, the more density, so they occupy high energy states, and if below 70 eV, then more and more of them would have velocities that would allow them to escape from the galaxy, and we would not have enough dark matter in the galaxy. So all of these reasons, the standard model neutrinos are not the dark matter. They are dark matter, but not the dark matter, not this 25% of the energy density of the universe. So here is going through, I use a thing, define the model, see a candidate. So the KSM, just a name. I take the standard model and increase the symmetry by imposing a Z2, which is not broken in the vacuum. All the standard model fields are Z2 even, and I add a single real beyond the standard model scalar field that is a singlet of the standard model group and is odd under the Z2 symmetry. Okay, that's perhaps the simplest example of a model with a dark matter. So I have the standard model plus terms with the chi field, kinetic, quadratic, since it is Z2 symmetry, no trilinear force, and it couples to the Higgs. It's very important these things are able to couple to the standard model particles, and this is the only, with the features I described or imposed, the only such term. So it's a 1-1-0 representation, no color, no electromagnetic charge, and it's stable. I impose the Z2 symmetry. This is the lightest, the only Z2 odd particle. So it's stable. Can it be the dark matter? So now I skip calculations. We have its properties. We can calculate its relic abundance at present, and we find that, so we know from following its history what should be its cross-section. Okay, two things. We know what should be its annihilation cross-section into standard model particles in order that it will give the right contribution to the dark matter. So this comes from two chi particles going into two standard model Higgs particles, which the model allows. We know the dependence of the annihilation cross-section on the parameters of the Lagrangian, and the requirement is that the mass of this thing over its coupling, the quartic couplings to the Higgs boson, is of order 3 TeV. So if this is, let's say, 0.1, then this should be 300 GeV. If this is 1, it should be 3 TeV, but just around the corner. So if its mass is not far from the electroweak breaking scale, then this is a viable dark matter candidate. This is called the WIP miracle because the required annihilation cross-section is of the order of the weak interaction cross-section. As I said, this comes from completely different ingredients in the calculation. And so looking for such things is an ongoing experimental effort. This is just the simplest example. I know I went through it fast to tell you why WIMPs are well-motivated candidate. If there is new physics at the TeV scale, then it could very well give us the dark matter. Okay. Sorry if I'm going fast, just the main things. So there is more matter than antimatter in the universe. All structures in the observable universe, stars, galaxies, clusters, this thing here are made of protons, neutrons, electrons. I'm made of protons, neutrons, and electrons. No structures are made of antiprotons, antineutrons, and positrons. And we know that observationally, okay? So there is observational evidence for that. Antiparticles come only, let's say, when cosmic rays hit the atmosphere, then particles and antiparticles are produced also in accelerators. The antiparticles are very soon absorbed and in the detector or on Earth and disappear. So this inequality is the baryon asymmetry of the universe. It's usually the number density of baryons minus the number density of antibaryons, normalized to the number density of photons. Astrophysicists, cosmologists put a subindex 0 to say at present time, close to 10 to the minus 9. So for every photon, there is, or for every 10 to the 9 photons, there is 1 proton in the universe, which means roughly that on average in the universe, in every meter cubed, there is 1 proton. Here there's quite a lot more, but not on the average in the universe. Or translation of that is that baryons, protons and neutrons, contribute to the energy density of the universe about 5% of the total energy density. And we have strong reasons to think that the universe started with an equal number of particles and antiparticles. And so this inequality should have been generated dynamically from processes along the history of the universe. And this dynamical generation, that's what we call baryogenesis. There could be here some dependence on the initial conditions. but I will assume that indeed the initial conditions were equality for two reasons. One is this principle of simplicity that I mentioned. In order that this asymmetry will be in the initial condition, it must be fine-tuned initial condition. They should be almost equal, but not quite. And the second reason is that we think that there was inflation along the history of the universe. And if there was inflation, then when inflation ended, there were zero baryons and zero antibaryons in the universe. So again, equal quantities, and it was only later dynamically generated. I will skip how we know the baryon asymmetry, and then Andrei Sakharov, a Russian physicist, first very precious to the Soviet regime, and then opposing the nuclear development, become less popular with the regime, the Soviet regime, and they put him in exile in a little town called Gorky. And sometimes when you are alone and with your thoughts, you come with very good ideas. And there he understood that there is a list of necessary conditions for baryogenesis, for the dynamical generation of baryon asymmetry. And if your paper is not cited as much as you think it deserves, you can get encouragement from Sakharov's story, because for the first 10 years after it was published, it had 0 citations, and by now it's one of the most cited papers in particle physics, with tens of thousands of citations. The reason was, I think, is that it was thought that baryon number is not violated in the standard model, and when it was understood that it is violated by non-perturbative effects, which we could not see when we wrote our Lagrangian, then suddenly his conditions became relevant. So first is baryon number violation, because if you start with a universe of baryon number 0, and there is no baryon number violation, then forever it will be 0, equal number of baryons and antibaryons, so that's clear. C and CP violation, particular CP violation, because if CP is a good symmetry, that any process that changes the baryon number in one direction has a CP conjugate process that changes the baryon number in the opposite direction, and they proceed in equal rates, and so no baryon asymmetry is created. And the third, a little bit more difficult to explain, is that there must be an instance of departure from thermal equilibrium in the history of the universe. The standard model qualitatively has all 3 conditions, even it's the full theory of nature. U1 baryon number is something called anomalous symmetry, which means that there are non-perturbative processes, not ones that you can describe by Feynman diagrams, which violate baryon number. Part of what we've done here is to explain that charge conjugation is violated by the weak interactions, and that with regenerations also CP is violated. And standard model physics create a phase transition, the electroweak phase transition, at temperature of about 100 GeV, when the vacuum expectation value of the Higgs field changes from 0. Sorry. It was 0 at early times because the scalar potential at finite temperature has additional contributions from interaction with the thermal bath around it, which makes the minimum at 0. It's a positive contribution to the quadratic term. At 100 GeV, the negative mu squared overcomes the temperature-dependent contribution, and then we go to the minimum that we know and love, where the symmetry is spontaneously broken. So that's a departure from thermal equilibrium. Turns out that of these 3 conditions, the one that is okay is actually the one least expected, baryon number violation. Again, a temperature higher than about 100 GeV is a fast process and can create a lot of barrier number violating interactions, even though they look quite complicated. The simplest of them involve 9 quarks and 3 leptons in one interaction. So if barrier number is violated and no barrier number violation after 10 to the minus 11 seconds, as far as we understand. So this is the latest time that baryogenesis could occur. If it occurred at that time, it's called electroweak baryogenesis, and the physics of it are a probe of the universe at 10 to the minus 11 second. Leptogenesis, one I mentioned before, by the way, is a probe to the universe when it's younger than 10 to the minus 27 seconds, which is rather impressive proximity to the Big Bang. CP violation in the standard model fails miserably because we want to explain an asymmetry of order 10 to the minus 9, and CP violation introduces a suppression factor related to the values of the quark masses and some entries in the CKM matrix, and this provides a suppression factor of 10 to the minus 20, which means that the CP violation of the standard model gives a contribution that is completely negligible to the baryon asymmetry. And also, once we learn that the Higgs is heavier than 70 GeV, in which case the phase transition would be okay. Once we learn it's at 125, and it's not a first order phase transition, but a smooth crossover, and so we need also a modification of that. So yeah, so what I want to say here is that this is exactly the things that we hope cosmology to teach us about particle physics. We learn 2 things. First, we learn that there must exist sources of CP violation beyond the Kobayashi-Maskawa phase of the standard model. And the extra phases that we got in the NSM, when we introduced these heavy sterile fermions, those that do not transform under the standard model gate symmetry, that is an example of such source of CP violation. And the second thing is that we learned that there must be one of the 2 things. Either there is another departure from thermal equilibrium beyond the electroweak phase transition, or the electroweak phase transition itself is modified probably by a scalar sector that is richer than just the one Higgs doublet. Okay, so this is exactly providing us in a test in a region that we did not yet explore in our labs. And it not just tells us that the standard model is incomplete, it tells us at which ingredients of the standard model needs to be extended and have some new physics relevant to them. So that's the value of this wonderful experiment that was prepared for us particle physicists. Okay, I don't have time to go into baryogenesis because I also want to summarize. So you're welcome to read the slides on that. I will not try to rush and go over them because it's not exactly a chapter, but there is a summary. And one last transparency. So this is already, the red is now behind the formal chapters. So a quick reminder. We gave a definition of the standard model, the 4 red lines. We need only to define the scalar and fermion content. The spin 1 particle content is dictated by the imposed symmetry. We learn from this the spectrum, the force carriers, and the fermions, matter particles. We learn about the interactions that the standard model describes. and the qualitative features that follow from the definition. We didn't need to make a measurement on the way from the definition to saying that these are the properties, a lot of predictive power. We identified the accidental symmetry. We counted parameters. We gave a possible list of these. We saw in particular that CP is violated in this model. We told a few failures of the standard model, neutrino masses, the barren asymmetry, dark matter. These, for me, are the three most convincing things, but there are also theoretical considerations. The model requires fine-tuning of the Higgs mass squared and of this non-perturbative term theta QCD. The structure of the Yukawa couplings with smallness and hierarchy, the possibility that the gauge couplings unified are perhaps clues to physics beyond. And the main experimental program that is now going on and testing some of these ingredients is the Higgs program. A priori, the Higgs program could also give us hints about the dark matter and about the baryon asymmetry in various ways that I did not describe. But I would say that almost any new measurement of the Higgs tell us something new, give us evidence to something new. It's really an exciting field of learning new measurements. I'll skip that, skip that, skip that. And this is the concluding thing. So what about the future of particle physics? It's up to you, okay? You are the future. Thank you. Yeah, I think we lost Poonam, so there is no someone in chief. I finished, I surprised her, I finished on time. Yes.
So, in your PDF on the cosmological tests, we saw that like the cosmological parameters can give a bound on the neutrino mass.
Yes.
Yeah. So, is that bound dependent upon the model that we use for the cosmological model that we use, or is it model independent?
Yeah. So, as far as my understanding goes, there is some what's called degeneracy between the neutrino masses and some other parameters of the cosmological model. So, yes, there is dependence on the cosmological parameters. I think that there are kind of standard values of what are the cosmological parameters, and from these, the bound on neutrino masses. So the bound is a bound on an upper bound on the sum of the light neutrino masses, and it's of the order of 1 electron volt or a little bit smaller, stronger than that, so it's competing with the direct experimental bound at present from Catherine. I think it's not a strong dependence on the parameters. However, if we find that our standard cosmological model needs to be fixed, not by sending parameters, but by something deeper, then probably this bound can be strongly affected. So that's my feeling, but it's not a very rigorous answer. It's my amateur understanding of that.
Okay, sir. I have just very naive question. When we talk about neutrino, we say that the neutrino is the second most abundance particle, and we say the photon is the most abundance particle in the universe. But if we look at the space, we see that dark matter is everywhere. Why don't we say that about the dark matter particles?
Yeah, because the density, okay, the density of the dark matter. So, for example, also even the baryons contribute much more to the energy density of the universe than the neutrinos, and yet the neutrinos are much more abundant. Okay, I think I said the neutrinos, we have 110 in each centimeter cube. Proton, we have 1 in every meter cube. So the contribution to the energy density is number density times mass. And both the photon and the neutrinos give very small contribution, even though they are the most abundant, because photons are massless and they contribute via their average energy, which is about 10 to the minus 4 electron volt. And neutrinos have mass of order 10 to the minus 2 electron volt, which is also very small. Compared to the baryons, 1 GeV, it's 10 to the 9 electron volt, so 11 orders of magnitude heavier than the neutrinos, and 13 orders of magnitude more than the average energy of the photons. And so it's one thing abundance, which is the number density, and another thing that contribution to the energy density.
Hello, sir. Hello, sir. Hearing? Hello, sir. Are you hearing me? Sir, are you hearing me?
I hear you, yes.
Okay.
If you
So-
put it close to your mouth,
Okay.
remember to do it, yes.
So my question is,
Not so close, it seems. Yes. Or Poonam will transmit it, yes, okay.
so my question is from you have shown that there is rotation in the galaxy, right? In the observation, galaxy rotation in the curve, you are showing that the velocity goes on increasing while increasing the distance. So first thing I want to ask is, from where the distance you are measuring from? I mean, you are talking about galaxy, right?
Can you repeat it more?
So
Helena? Go
his
back.
question is basically about the galaxy rotation curves.
Yes,
And in that, he's asking, what is the point from which you are measuring the distance? Right? First question is that.
is what again?
You
Sorry.
just keep it like this, it will work. Try.
Just a minute, I'll show the rotation curves and then I hope to understand the question.
Yes.
Yes, so what
Yes.
exactly is the question
So-
about this?
What does from where the distance is measured? I mean, in the on the x-axis.
X-axis,
This yes.
distance from the center of the galaxy in light years.
In
Distance from center
okay,
of the
that is
galaxy
in light
years.
Light years. So from where you are measuring the distance? From where to where?
What from?
From the center of galaxy. So
Yes.
the velocity of what? That is also from the galaxy. Oh,
So the stars go around the galaxy,
okay.
and this is the velocity in which they go around the galaxy. And once you are in a distance larger than where all the luminous matter is, which is about up to here, there is very little luminous matter outside this, then the velocity should go down like v squared equals 1 over r. If it is going to a constant, it means that for some distance, the velocity square goes to a constant, which means that there must be mass there which goes like r, or if you want, there must be matter density there, which is going like 1 over r squared. Such a matter distribution would explain why the velocity are there. This all comes from just gravitational
That's what.
attraction.
Okay. Yes. Thank you. Clear.
Clear. It's clear. Okay. Any other offline participant.
You skipped QCD part.
QCD?
QCD.
Yes.
In all this, when we see future of the particle physics,
We see what of the
QCD, quantum
Yes, QCD.
chromodynamics. So, say perturbative QCD or QGP or Coulomb plasma, the phase diagram of the QCD. But I mean, where do we? Where do we see the contribution of the quantum chromodynamics, say perturbative quantum chromodynamics, say structure function, understanding the spin of the proton, and
I'm not, we see the effects of QCD everywhere.
okay,
Okay, so first of all, we see protons and neutrons are made out of 3 quarks. We see a complete spectrum of hadrons made out of quarks. We see productions of 2 jets, 3 jets. We understand the 3 jets as gluon being, so not just QQ bar,
yes,
but quark and gluon. We see the production of the Higgs in the LHC
Gluon.
coming mainly from gluon-gluon fusion.
yes,
We see that the proton, as we explore it with higher and higher energy, we see a more and more prominent component of a gluon inside the proton.
yes,
We see the effects on QCD just, I don't know, really everywhere. So when we see the Higgs decay to bottom anti-bottom compared to tau plus tau minus,
Yes,
it's
yes,
not
yes.
simply 3 times mb over m tau squared.
Yes.
It's modified, and it's modified because QCD effect on the Higgs to BB bar. We see that the mass of B at the scale of m Higgs has run much more than the mass of the tau to the mass of the Higgs. And that's again because of QCD effect. So we see it modifying Wittig interactions, structure functions, binding hadronic spectrum everywhere.
and
But not everywhere we can calculate it, okay?
okay. And there was a Higgs decay to CC bar because there's a long-standing problem of the production of the heavy cauconiums. We really don't understand. There is some inconsistency in
The Higgs to CC bar,
not just production of the charmonium, and then there is also a 2 sigma error that is there in the Higgs to CC bar. Do we have a role that QCD, non-perturbative QCD effects?
I don't think so. I think that this 2 sigma is likely to go away with
Okay.
higher statistics. And my experimentalist friends, I have quite a few experimentalist friends, whenever I take seriously a 2 sigma effect as a deviation from the standard model, they are unhappy with me. They tell me I should not. Until it reaches 3 sigma, this is the standard model. That's what they insist. Once it goes over 3 sigma, they allow me to be interested and perhaps write a paper. But, the consensus in the community is that you need 5 sigma for a discovery of something which is not standard model. I think it's accepted that a 3 sigma consistent with the standard model is considered a measurement, but for a discovery you need really 5 sigma. And during the years that I've been doing particle physics, I've seen quite a few effects that were above 3 sigma and went away. I'm yet to see an effect of more than 5 sigma that would go away with statistics, because there were some systematic effects that were later understood, and also these very, very few occasions. So I think really we should wait for 5 sigmas for discovery and 3 sigma in order to take seriously the possibility of possible anomaly compared to the standard model. And the charm is not there. The Higgs to charm is not there yet, and I strongly believe that it will converge to the standard model value.
Okay.
But this is a belief, okay? This is not.
Thank you so much, sir.
Any other?
Hello, sir. Hello. In standard model, baryon asymmetry, baryons can be possible, but not enough to explain the baryon asymmetry of the universe, right?
By many orders of magnitude, yes.
Okay. But for generate baryogenesis, we need three conditions out of thermal equilibrium and CP violation, and the third one is, I think,
Baryon number violation.
baryon number violation. Those baryon number violation and CP violation is possible, but out of thermal equilibrium is only possible first order phase transition.
What's the second sentence? Sorry, I didn't get.
The out of thermal equilibrium condition in standard model case only possible by the first order phase transition. I think so.
By the
First order phase transition of electric phase transition.
electric phase transition, yes.
So, and from experiment we know that it is not first order, it is second order.
It's smooth crossover. It's not the first order phase transition.
So, what is the other source of out of thermal equilibrium in the standard?
So, for example, in leptogenesis, when these heavy sterile neutrinos, these states that are introduced, N in the model NSM, when they decay, they are out of thermal equilibrium.
But it is beyond standard model, no?
Yeah, that's beyond the standard model.
But in the standard model,
Okay, as I said, there are two possibilities. Or there are different departures from thermal equilibrium, for example, in leptogenesis, or the departure from thermal equilibrium is still electroweak baryogenesis, but its features are changed because of physics beyond the standard model. For example, in a 2 Higgs doublet model, you could have still a first order phase transition instead of the smooth crossover of the standard model. By the way, if the Higgs were lighter than 70 GeV,
then it is first.
Then even the standard model electroweak phase transition would have been first order. So this was something for experiments to decide. But yeah, you can have a more complicated scalar sector, and then the form of the scalar potential would have been modified in such a way that the electroweak phase transition could still be, but not with purely standard model physics.
I've never seen a picture with elliptical galaxy.
You don't see a picture of?
Elliptical galaxy. See, there are some spiral galaxy.
I don't know. What? Yeah.
Just ask me. I really like a set of excellent lectures. Just to say that today we are celebrating the National Science Day on the memory of Nobel laureate Professor C.V. Raman.
Professor?
C.V. Raman.
Okay.
Yeah, and I think there is no other better way to celebrate the National Science Day with the looking at the bright future of the particle physics.
Okay. Thank you. Yeah. Celebrate with you.
He has a question.
Hello. Just while you were showing the large scale structure formation, you mentioned it's 10 to the power 5 years, but shouldn't
large scale structure? I didn't.
Initially, I think 5th or 6th slide.
I don't think I showed the line.
You miss
Okay.
5th, 6th slide. Yeah, the one.
Here? No.
The previous one. Shouldn't large scale structure be after CMB? Large scale structure formation should have been after CMB, right?
Yes.
So
okay. So it's a question I tried to find with my cosmology. Okay, let me say this. While T here equals, we know the date, while here we know the range, while here we have an upper bound. This is a long procedure of the small anisotropies that are created in the background and how they develop and how the potential changes and attracts more particles. So it's a long process. And I could not find consensus about reference of exactly quoting. So this is more when it started, the seeds of that.
Okay.
But the process goes on for some time.
For
until
quite some
reach the
time.
present. Yeah, so it's not that at that 10 to the 5 years, the large scale structure, the seeds for that, the quantum fluctuation that preceded this started in earnest. That's, yeah.
Okay. Thank you.
Is there any other? Okay. There's one online question. What are the implications of CP violation in lepton sector?
Yeah, that's yeah, so the implications of CB violation in the lepton sector, well, first of all, it affects neutrino oscillations, so that's low energy and can be measured in principle in neutrino oscillations experiment. Perhaps more interesting is the effect that allows it to drive, or this is the condition of new sources of CP violation, and so a heavy Majorana neutrino state, one of these ends, can decay to a Higgs and a lepton, and that can interfere with that another, or through a loop where the other N2 or N3 appear in the Higgs. So the Yukawa couplings here involve also N2 and N3. This loop diagram interferes with that, and that would be the source of CP violation. It creates a CP asymmetry, the creation of a lepton and a Higgs versus the creation of an anti-lepton and anti-Higgs if you want. And one can calculate the CP asymmetry. It depends on the mass ratios between the lightest and the next to lightest heavy neutrinos, and it depends on the Yukawas of the Higgs with a heavy and a light neutrino, this matrix Y and E, and this is calculable, and I think it's allowed that this asymmetry would be rather small and still leptogenesis would go on successfully. And so with these numbers and Yukawas of order 0.1 and mass ratio of order 0.1 and this area over 16 pi, there is no problem in creating the required asymmetry for baryogenesis. So that's why CP violation in neutrinos is very interesting. Could solve also the baryon asymmetry puzzle.
Last chance to ask any question. Huh?
You can write to me.
You can, of course, yeah.
Yes, you will find easily my
In this school.
email address, and if you write, I will answer. Including I may answer, I don't know, but I will answer. Okay, so.
Okay. So I see no raised hands. So yeah, I think the last 5 days or 4.5 days have been really like magical. Revisiting the standard model by these excellent set of lectures from Yossi, and I think of course the senior people revisited the standard model and really thoroughly enjoyed. The younger people the not so young people learnt things, and the very young people saw that there is a lot to learn, right? So those are sitting at the back. Yeah, I mean the world is very beautiful, and yeah, we have to go ahead but the beauty you can probably appreciate. So thank you very much, Yossi, for sparing your time and coming and giving us this overview.
So before, so maybe I'd say just 2 words, no, but
Yeah.
I enjoyed this week at least as much as you did, okay? This interaction with you was really highly enjoyable to me, both on the professional question and on the personal. So I just want to say she appreciates that I gave my precious time, okay? It's a very enjoyable experience to me. So I also thank you for this week. It has been very nice. As you could have sensed, I think, that it's nice also for me. So thank you. That's it.
Let's give him a big round of applause. Yeah. So I would just request maybe 1 or 2 people to share what you felt, just to have an idea. We are also circulating a feedback form, but just maybe quick 1 or 2, 1 male and 1 female. You can share your experience. Who wants to go first?
I shared my experience, so 1 mail is done. No?
No.
No, okay.
Yeah. Who wants to go? Siddharth? If you don't raise your hand, I'm going to.
So for me, like, actually, I was supposed to come with my friend here, but then he bailed in the last moment. So I was actually kind of sad that. Okay, I guess.
Why? Let him speak from there. He will feel more comfortable.
What he is trying to say.
Yeah. So like, anyway, so I was in the, like, I came to the workshop and I thought that, okay, so this is a workshop on standard model. And the thing is, like, I have already had experience like going through standard model before. I also have had courses and like preliminary courses in quantum field theory. But the thing is, like, I still decided to come here anyway because I know that these things are like such things that you just cannot understand when you read it for maybe the first time or the second time. So every time you read the same thing over and over again, you would see that there's something new that you can learn, right? So for example, I did not know anything about these accidental symmetries, so they're completely new to me. So that's why I think also like interaction with the people here and also Yossi sir. So it was really a great experience for me. Like, I wasn't bored at all. I thought I would be bored, but I wasn't. So thank you.
Okay, thank you.
Among the female?
My God.
Hi, yeah. I'm in my final year of PhD. Like, I have a pressure also, like, I have to submit my thesis also before June. And now, in that case, like, I feel very fortunate, like, to meet Yosef sir and discuss physics. Now, I have a very, like, gaps in a standard model, like, the few things. Now, I feel that, like, I'm in a correct way. And, like, and first of all, I would like to really thanks to Yosef sir, like, yeah, thank you so much, like, for these lectures and all discussion. Yeah, thank you.
Okay, so any other? The youngest of the lot. Come, Sambhavi. She's a bachelor student. You can share what you felt. Yeah.
Hi. So I have recently started my journey with particle physics itself, and so this course was extremely heavy for me. I started 6 months back. I have just got into group theory, so this was like extreme stuff for me. But now I have a really well structured skeleton for me as to how I need to proceed with this. So thank you so much for that. But something that I really want to appreciate you for was seeing your work with women in science has been really refreshing. Like, I cannot even explain to you the impact it has had on me, and it's insane. So thank you so much for like standing up for us, and I hope to see you soon.
Okay.
Thank you.
Great. So, oh, Ram, please.
It's more and more embarrassing. Okay.
Yeah, so I'm a teacher in undergraduate college, and yeah, so very often a student come to me, sir, I want to do. I mean, we have culture of calling sir to the teacher. So we want to do project with you, and then I would say that I don't know, maybe it's too heavy for you to work on uh, standard model or beyond standard model physics. So I usually used to refuse them, and in 4 or 5 years, only one student could do project with me, and that was to on neutrino physics purely. Uh, so yeah, I mean, I got to know about this Gyan course Poonam shared, and I just saw it, and I was just doing another FTP program in Delhi University, and I was missing my classes. So I thought I will just pass because I anyway know the standard model in 5 days. How much is Yossi going to cover? I have spent like years to study it, so I will pass. But Poonam insisted that you should come. Yossi is an excellent speaker, and that we saw. Oh, thank you, and thanks to Poonam that she insisted that you should come. What I learned here, um, uh, I learned that now I will not say my students that it's too heavy for you. Now I can say, okay, even if you do not know quantum field theory, we can start working, and I can actually directly tell them go and watch those lectures, and then we can start talking about it. So yeah, I mean that was really nice that I got to know that you can talk about external model even without knowing that much of quantum field theory. So yeah, I mean that I definitely learned. So thank you.
Thank you.
Okay, so then we close. Yeah.
Yeah.
Okay. Thank you very much.
My
And
pleasure.
as they say in Israel, Toda Rabba.
Yes, that's in Hebrew.
Yeah.
Yeah. Mhm. My pleasure. Okay. That's it. We are done.
This part.